In this video, I'd like to talk about transformations of functions. All right, there are several different types of transformations that we can have. For example, we can have vertical and horizontal shifts, vertical and horizontal reflections, and vertical and horizontal stretches and compressions. All right, so there's a lot for us to look at, so I'd like to dive into it. All right, let's get started. Okay, here we go. Transformations of functions. The first transformation we'll look at is a vertical shift. Okay? Given a function f of x, a new function g of x equals f of x plus k, where k is a constant, is a vertical shift of the function f of x. All right? So we have some function f, and we have a new function g that we define by shifting f up by k units. All right? If k is positive, then the graph will shift up. And if k is negative, then the graph will shift down. Okay? So let's see an example. All right? Here we have the function f of x equals the cube root of x. All right? We get the curve that looks like this. All right? But the question is, what would the function look like if we took the cube root of x and added 3 to it? All right? We know from the previous screen that since 3 is a positive number, that means it's going to shift this graph. It's going to shift this graph up by 3 units. All right? So take a look at this point right here. We can see that it passes through the origin, right? It passes through 0, 0. And then up here, it shifts up to 0, 3, right? It passes through the point 0, 3. So the entire function has been shifted up by 3 units. All right? And one thing that's important to note is that we're adding 3 to the outside of the function. All right? We're adding 3 to the entire thing, right? Adding 3 to f. Okay? With a horizontal shift, we don't add something to the whole function. All right? We actually plug something into the function. All right? Given a function f of x, a new function g of x equals f of x minus h. All right, so we're plugging x minus h into the original function f to get this new function g. All right, a new function g, where h is a constant, is a horizontal shift of the function f of x. All right, if h is positive, then the graph will shift right. If h is negative, then the graph will shift left. All right, so let's see an example of this. All right, let's look at the same function. Let's look at f of x equals cube root of x. All right, instead of shifting this thing up or down, right, this time it's going to shift either right or left. All right, so the question is, what would the new function look like, right? What would the transformed function look like if we were to plug in x minus 2? All right. Notice the difference between horizontal and vertical shifts, right? With a vertical shift, we added a constant to the outside of the function, right? But with a horizontal shift, we plug x minus 2 into the inside of the function, right? What does f say to do? It says to take what you're given and take the cube root of that. All right, so we'll take x minus 2 and take the cube root of that. All right, and that will result in a horizontal shift 2 units to the right. Okay, once again, pay attention to the origin, right? This original function passes through 0, 0, and this new transformed function passes through 2, 0. All right, and the entire graph has shifted 2 units to the right. All right. Now let's look at what happens when we combine vertical and horizontal shifts together, right? When both are happening at the same time. All right. Given the function f of x equals x squared, sketch a graph of g of x equals f of x minus 2 plus 1. All right. So we have this function here, right? We have the parabola f of x equals x squared, all right? And the question is, what's going to happen when we plug x minus 2 into the function f, and then when we add 1 to that entire thing, all right? That sounds to me like that's going to be a horizontal shift 2 units to the right, and a vertical shift 1 unit up, all right? So our new function g of x is going to be equal to x minus 2 whole thing squared plus 1. All right? When we plug x minus 2 into the original function f, right, we take that and we square it, right? That's what the function says to do. So we have x minus 2 squared, and then we add 1. So we get plus 1. All right? What does that function look like? Well, just like we said, it's a horizontal shift 2 units to the right, and then 1 unit up. Okay, so this is our new transformed function g. All right, next, let's look at vertical reflections, okay? Given a function f of x, a new function g of x equals negative f of x is a vertical reflection of the function f of x, all right? The reflection occurs about / over / through the x-axis. All right, so you can use any of these 3 words that you want, all right? They're all saying the same thing, right? The reflection occurs through the x-axis, all right? That's the way I like to say it. Let's look at an example, okay? Here's the function f of x equals the square root of x. The question is, what does the function g of x equals negative square root of x look like? All right, we're slapping a minus sign in front of this original function, right, to get this new function g, which means that it's a vertical reflection through the x-axis. All right, so we're going to take this swoosh thing and reflect it through the x-axis. Okay, so we can imagine that the x-axis is a mirror, and we get our new function that looks like this. It looks like this. All right, so that's what a vertical reflection looks like. A horizontal reflection is very similar. All right, given a function f of x, a new function g of x equals f of negative x is a horizontal reflection of the function f of x. All right, so the reflection occurs through the y-axis. All right, so we imagine that the y-axis is the mirror, and our function is reflected through that. All right, so notice this is a horizontal reflection, right? Any horizontal transformation involves plugging something into the original function. All right, we're plugging in a negative x into f. All right, whereas with vertical transformations, right, we do something to the outside of the function, right? For a vertical reflection, we take the whole function and we multiply it by -1. All right, so let's see an example of a horizontal reflection. All right, we're just going to take a look at the same function, all right, the same function we had in the previous example. F of x equals the square root of x, all right? The question is, what does this function look like? G of x equals the square root of negative x. All right, so we're plugging negative x into the original function, and we're getting this new function g. So this is going to be a horizontal reflection through the y-axis, all right? So the swoosh, instead of extending this way, right, it extends this way to the left, all right? And notice you can't take the square root of a negative number. All right, so this function is only defined for negative x values, right, because negative is a positive number, all right? So this function is only defined over here. But that's not really the important part. The important part is that you're transforming the original function f by plugging a negative x into it, right? You're taking the square root of whatever you're given, which is negative x. That's going to give you a horizontal reflection through the y-axis. Next, let's talk about vertical stretches and compressions. All right, given a function f of x, a new function g of x equals a f of x, where a is a constant, is a vertical stretch or vertical compression of the function f of x. Okay, So this is a vertical transformation, so we're doing something to the outside of the function, right? We're taking f and we're multiplying a by the entire thing, all right? So the value that we choose for a matters a lot, all right? We have three cases, right? We're breaking this down into a case-by-case basis. If the number a is greater than 1, then the graph will be stretched. If a is in between 0 and 1, then the graph will be compressed. Finally, if a is a negative number, right, if a is less than 0, then there will be a combination of a vertical reflection with a vertical stretch or compression. All right, so it'll have two things happening at once. Two transformations. All right, let's see an example for each of these cases. All right, so let's start with a equals something greater than 1. All right, that should give us a vertical stretch. All right, so let's look at this function again. F of x equals the cube root of x, and then ask what this new function will look like. G of x equals 3 times the cube root of x. 3 is greater than 1, and we're multiplying it by the entire function, right? So this is going to be a vertical stretch, and it looks like this, right? Imagine taking this function here and pulling up and down at the same time, right? It's stretching up and it's stretching down. Okay? So this is what the transformation looks like. For a vertical compression, what we would have would be something like this. All right? This time, the number a is in between 0 and 1. Okay? So we have g of x equals 1/2 times the whole thing, right? Times cube root of x. All right? So this is what a vertical compression looks like. All right? This time, instead of stretching the curve up and down, right, it's being pushed down by both directions. All right? So this curve is being squished down to give us something that looks like this. All right? That's a vertical compression. And here, let's look at an example where this number a is negative, right? We have -2 being multiplied by the cube root of x, all right? Because -2 is a negative number, what's going to happen first is that this thing is going to be reflected vertically across the x-axis, right? And then stretched up and down, right? To give us something that looks like this. All right? So if a is negative, right? If this constant here being multiplied by the function, if this constant is negative, you'll get a reflection, and then you'll get either a stretch or a compression, right? In this case, it was a stretch. Okay? Next, let's look at horizontal stretches and compressions. All right? This time, instead of multiplying f by some constant, right? Instead of multiplying the entire function by some constant, right, we're going to plug something into the function f, right? We're plugging in b of x, where b is a constant, all right? That new function is a horizontal stretch or horizontal compression of the original function f of x, all right? Once again, we're going to break this down into a case-by-case basis. If b is greater than 1, then the graph will be compressed. If b is in between 0 and 1, then the graph will be stretched. And finally, if b is less than 0, right, if it's a negative number, then there will be a combination of a horizontal reflection with either a horizontal stretch or horizontal compression. Okay? So let's look at those cases. All right, here we have the function f of x equals x squared. We want to know what the new function g of x equals 2x whole thing squared looks like. All right, we're plugging 2x into this original function f, right, which says to take what you're given and square it. All right, so we have 2x whole thing squared. All right, because 2 is greater than 1, the previous slide will tell us that we have a horizontal compression. All right, so it's being squished horizontally from both ends, right? this is what it looks like. All right. For a horizontal stretch, we're going to plug 1/3 x into the function f, right? So we're taking 1/3 x and we're squaring the whole thing, all right? And because 1/3 is in between 0 and 1, the function will be stretched horizontally, all right? So it's being stretched to the left and the right, all right? And it looks like this, all right? One more case to look at, all right? And that's what happens when we plug bx into the function f, and b is a negative number, all right? B is -2 in this case, all right? So the first thing that does is it causes a horizontal reflection, but look at this function, right? It's symmetric about the y-axis, so when you reflect that horizontally, it doesn't do anything, all right? So nothing happens there, but then a horizontal compression also takes place, all right? So the function is being squished from the left and right, and it looks like this. Okay? Let's look at an example, all right? Let's see an application. A function p of t models a population of fruit flies. Compare this population to another population, q, whose growth follows the same pattern but is twice as large. And then we're asked to sketch a graph of q of t. So here's our function p of t. All right, it's only defined for positive t values. All right, and our textbook doesn't give us units for t. Right, I don't know if t is measured in hours, days, or years, or whatever. But this is what the function looks like, nevertheless. All right, p, right, that's the number of fruit flies, and t is time, okay? So we want to know what this other population q looks like, all right? And we're told that the population is twice as large, all right? So to transform this function p, that's what we're going to do. It's a transformation, right? We're going to transform the function p into a new function q. All right, and we don't need the function formula. All right, what we can do is we can actually just take a look at some points. All right, let's take a look at a few points. P of t passes through 0, 1, and this blue point 2, 2, and this red point 4, 1, and this green point 5, 0. All right, so q has a population that's twice as large. All right, so we can take each of these y values and multiply them by 2 to get new points, and we can declare that the new function q is going to pass through those new points. All right, so let's start here with the black point 0, 1. All right, 0, 1, we're going to take the y value and multiply it by 2 to get 0, 2. All right, we're leaving the x value the same. All right, and we're taking the y value and multiplying it by 2. Okay, because the population is twice as large. All right, we'll get the black point 0, 2, and we'll get the blue point 2, 4. Okay, right, we're multiplying 2 by 2 to get 4, and then we'll also get the red point 4, 2. Right, we'll multiply 1 by 2 to get 2, and finally we'll get the green point 5, 0, right? 0 times 2 is still just 0. So the function q passes through these 4 points, and we're told that the growth follows the same pattern, all right? So it curves up, and then it decreases and decreases, all right? So we can draw the function q of t, and we can see that it looks like this, right? It passes through these 4 points, and it follows the same growth pattern as the original function p of t. All right, so q of t is a transformation of p of t, namely, it's a vertical stretch. Okay? That does it for this video. Thank you for watching, and like and subscribe.